Okay, so as we start to study for diplomas, we can start reviewing thermochemistry and going through it. So if you are taking a look at this, one of the very first things that we look at is Q equals mc delta T. And this formula we use if you're just heating or cooling a substance. So this is not a reaction. So when you're doing this, you do have the mass of a substance, specific heat capacity of substance, and temperature change. This Q value will let us know if heat was given off or if we absorbed. So the other part that is a bit more of the theory is just that the original source of all energy is coming from the sun. And we also do want to know this reaction, or not this reaction, but this order. So from the sun's energy, we have photosynthesis that will harness that sun energy. Then we would have animals and plants eventually, it sounds awful, but die, and after time they will decay, and then that will make fossil fuels, and it can be harnessed to then eventually use, and this is just an example, like gas in your car. So here is a few our old diploma questions that just show that even though there's lots of information here, when it says the original source of energy, it's always going to be the sun. Another one, it looks like this might be set up for Hess's law or something along those lines, but then it's asking for the original energy source. We know it's going to be the sun. Now, moving on from there, we started looking at enthalpy and molar enthalpy. So if we just have enthalpy or enthalpy of a reaction, you can think of it as the heat given off or absorbed, but then we also want to know that every reaction will have an enthalpy, and depending if you change the amount of moles, you will either have more or less heat being absorbed or released to the environment. So here's one example where we have a balanced chemical equation. We know that we have an exothermic reaction. So if you take that value out of the equation, because it's on the product side, you would make it negative. If it was on the reactant side, it would be positive. Because it's asking for the molar enthalpy of the nickel oxide within this reaction represents 3 moles. So you take this and divide it by 3. When you do that, you'll see your answer is this value C, the negative one. And so just be careful with that, remembering that if we take it out, the value will be negative. And if it's a molar enthalpy, you want to divide by the amount of moles of whichever species you're being asked for. Here's another one, but this one is a NH equals delta H question. And I know that because we have this balanced chemical equation with the combustion of methanol, and then it tells us that it's producing an enthalpy change. So in this equation, if energy is given off, that would be the delta H within this formula. Then this H here is always based on that reaction. So we're filling that in, and this one is a molar enthalpy, so it also gets divided by the amount of moles of whatever species you're talking about. And in this case, it's methanol, so we'd have to divide it by 2. So to set up this one, you'd have NH, I'm just writing the formula again, equals delta H. So N times negative 1,275.8 divided by 2 moles, because we have 2 moles of methanol, will equal the amount given off, which is negative 9.00 times 10 to the power 4 kilojoules. So we want to isolate N because we know that we can always go between mass and moles with molar mass, and that's what we're eventually finding. So we'll get N alone by dividing this all over to the other side, and at this point we get this value that's 141.08. This number will keep going, don't round too early, and we want to multiply this by the molar mass of methanol, which is 32.05 grams per 1 mole. So this step gets moles to cancel, and you end up with a fairly large number, 4,521.8, but that value is in grams. And here your unit is kilojoules. So we'll take this value, divide it by 1,000, converting your grams into kilograms, and your final answer will be 4.52 kilograms. Then We move on and we talk about how you can communicate your enthalpy. And just like we saw, you can see it within the equation, like this first point, but you can also take it out of the equation. And then depending if it's endo or exo, it would give you a sign. So if you have your enthalpy on the reactant side and you take it out, it is going to be positive, meaning endothermic. If you take it from the product side, it is going to be negative, meaning exothermic. So this next example is now showing that we understand enthalpies, and more importantly, molar enthalpies, because it's asking if we order this from the one that absorbs the most to the one that releases the most energy per mole of carbon dioxide, how can we order it? So if it's most absorbed, this would be the most positive, and we're looking, that would mean endothermic. So most positive, and then releases most would be most negative, so exothermic. So looking at the first equation, this value, positive 90.1, is on the reactant side. So if we took it out of the equation, it would still be positive 90.1 kilojoules. And this equation is representing just 1 mole, so we don't need to divide by anything. The second equation, it's on the reactant side, so if we take it out, it's going to be negative. Same idea, it's only representing 1 mole, so we don't need to divide by anything. Equation number 3, we have it on the written in delta H notation, but this value is representing 2 moles, so we want to divide it by 2, and this last one represents 3 moles, so we want to divide it by 3. Once we have each of our values, then your most positive was reaction 4, and then our next positive was 1, and then we're moving into the negatives. So the smaller negative was number 2, and the most negative was number 3. Here we still have another combustion reaction, right? We have sucrose, and it's in the presence of oxygen, and you're getting out carbon dioxide and water. So when they're asking if you were to write your energy as a term within the equation, because it is a exothermic reaction, we would need to have it on the product side so we can rule out the first two. And now, even though this reaction itself is an exothermic reaction, which is because it's a chemical reaction, would be potential energy, it's not asking you about the reaction itself, it's asking you about the water. So the water within a calorimeter is not what's being reacted, it's what's measuring the temperature. So the water, because it's a combustion reaction, is going to increase in temperature, and the molecules will move faster, and anything that has to do with movement will be kinetic. So this one would be C. If the reaction, or if the equation asked you about what was happening within the reaction, then we would have picked potential, because potential has to do with your chemical reactions. Moving on from there, we start to look at Hess's law, long and short. This first one is Hess's law short, and there's just a few little things here. One is this last one here is that even though we have standard heats of formation, that would be shown on page 4 or 5 of your data booklet. If you wanted decomposition, because you would have to flip that reaction, you just change the sign. So saying opposite energy, if it was positive, it's now negative. If it's negative, now it's positive. And the formula we're going to use, and I usually write this out a lot quicker or simpler, I just say delta H will equal products minus reactants. But what this is saying here is we're going to take the sum, right? This symbol here means sum of the delta H of the products and subtract the sum of the delta H of the reactants. So I have 2 examples I wanted to do here. One is just to point out that we need to be careful. So we have a series of equations, but then it's asking you just about equation number 1. And it gives you this information that the molar enthalpy of formation is going to be 21.7 kilojoules per mole. This means for only 1 mole. So when you look at equation number 1, we want to recognize that this is not a formation reaction. This is a decomposition reaction. So if we want the delta H for this reaction, we'd have to change this sign. So the delta H would actually be negative 21.7. And because this is showing you just 1 mole forming, and this has 2 moles decomposing, we'd also need to multiply that by 2. So your final answer here would be A, I believe. Just want to double check. Yes. And then moving on from this one, actually using Hess's law short in terms of the math, what you would want to do is look at, again, page 4 or 5, and you're looking at the standard enthalpies of formation. So if it's CH4, you would look that up, and it has a value of negative 74.6. NH3 has a value of negative 45.9. We don't need to do anything with this right now. We will in a second. It's asking us to figure out the enthalpy of formation of HCN. And then we have 3 moles of hydrogen. So we'd have to multiply the 3 by its formation, but remembering that any element by itself has an enthalpy of 0. So if I went to go set up my formula, and again, I just like to write it nice and simple, of products minus reactants, I know that enthalpy, it's given to me. When I take it out, because it's on the reactant side, it is a positive value. If it was on the product side, it would be a negative value. Then my products would be HCN, which I'm just going to call X, minus 0. 3 times 0 would just be 0. And then I'm going to subtract my reactants, which is negative 74.6, and we're adding negative 45.9. So now our goal here is just to solve for X. So we would just simplify this equation so that 255.6 is still there. And then we'll have X minus, and this is negative 120.5. You're subtracting a negative, so it would become positive. So we would then subtract that value of 120.5 to the other side, and you would find X equals positive 135.1, and it would be kilojoules per mole because there's only 1 mole. Now, if you're using Hess's law long, I always like to say it's like a series of puzzles. We're figuring out how to manipulate the puzzles to get to your target equation. So we want to remember these rules, that if you flip a reaction, you flip the sign, and if you multiply or divide your reaction, you also multiply or divide delta H. Then you add your reactions together. Everything that you don't need should cancel out, and then you can add your delta H for the net reaction. So the example I have here, we have a series of reactions, and I want to start by looking at placement. So I noticed we have this C2H5OH as a reactant, and in equation 1, it's also as a reactant. So I'm going to keep that as it is. But then I also want to notice that I have a 2 out front. So to make this reaction give me a 2, I'm going to multiply everything within by 2. I'm going to start rewriting it. So I have 2C2H5OH plus 6 oxygen. So I'm multiplying my 2 all the way through, plus 4 carbon dioxide, plus 6 water molecules. And now I'd also need my delta H value to be multiplied by 2. That's my first one. My second reaction, I want to notice that my 2C2H4O is a reactant, but in my target, it's a product. So I'm going to flip reaction 2, and I'm not going to do anything else with it because I want 2 moles and I have 2 moles. So when writing this one out, you have 4CO2 plus 4H2O. And actually, I should put these states here for just water since it's changing. Plus your 2C2H4O plus 5 oxygen molecules. Now, the last part that I would want to do is take a look at water. In my formula, I need water as a liquid, and I don't have any gases as my water. So what I want is this gas molecule to be canceled. And I also should add on my delta H here. So this is my first one. My delta H for this one, because I flipped it, is positive. Okay, so now my goal to get this one to cancel is I need to have 4 of the gases state on the other side. So I'm going to multiply this last equation by 4. So this value of 44.0 needs to be multiplied by 4. And I don't need to flip it. And what I'm going to notice now is everything I don't need will cancel nicely. So the carbon dioxide cancels, the water in the gas state cancel, my 5 oxygens will cancel with 5 out of the 6 oxygens, leaving just 1, and that's what I want. And 4 of my liquid waters as a reactant would cancel with 4 out of the 6 of the liquid water on the right. So now, even though it looks very messy, I have exactly what I need. I have my 2 C2H5O5, I have 1 oxygen, I have 2 water molecules, and I still had 2 of this big molecule here. So once I have that, then I can add all my enthalpies together. And when I do that, my answer is going to be C. Okay. Another big part of the thermochem unit is all about calorimetry. So not only do we have this formula, but we also do have bomb calorimetry, where we have NH equals negative MC delta T plus negative MC delta T. So if you do have bomb calorimetry, it's going to be a combustion reaction, but this first MC delta T will still be about the water. The other MC delta T would be about the container. And we just add that on. So going through it, the part that I like to emphasize is that specific heat capacity of water, because all our units will depend on that. And the rest, so we can plug it in and figure it out. So with this example, we have this information about, and we actually did a question using this information, but now we're using it with the calorimetry. So we have this information. It is about the combustion of sucrose. And even though a combustion reaction is usually bomb calorimetry, if it doesn't give you information about a container, you just treat it like a normal calorimetry question. So NH equals negative MC delta T. So within this question, we know the mass of the water. We know the specific heat capacity of water. We know the temperature change. And then on this side, we're solving for H, but we do know the amount on moles, which is nice, so we don't have to do an extra calculation here. So we want to get H alone. And when you do that, you're going to get a fairly large number. H is going to equal 3,875. Actually, I said that wrong. 3,875,750. As pointed out, though, this value here is joules per gram degree Celsius. So when we're solving for your enthalpy, which is a form of energy, that will be in joules. So to make it into kilojoules, we'll divide it by 1,000, and then we'll move our decimal, and we'll see our answer is D. There's a few other reactions you want to know. Sometimes a question can be nice to you and give you the reaction. Other times, it won't. So you want to have it memorized. So here's one just reiterating for photosynthesis, and then the opposite to that, cellular respiration. So when we're looking at these and knowing what they are, this one's nice to us, it's given, but again, it might not be. So when it asks us to accurately describe, I'm just going to skip right to the answer. Photosynthesis requires energy, right? Energy is a reactant, and cellular respiration produces energy. And that's true because it's produced. You can check the other ones. It's not going to work out. Nothing will match out. So just as long as we know the reactions, and if they weren't given to us, we have them memorized and we would be able to figure this out anyway. And then one of the last topics is about activation energy. So just to know what it is, it's that energy barrier that must be overcome for that reaction to occur. So we do have those typical, why does my pen not want to work now? Okay. Last PowerPoint decided to stop working, so let's try this one. So we got to activation energy. When I'm looking at this and just looking at the catalyzed reaction, all catalysts do is lower that activation energy. So if it's asking for the activation energy of the catalyzed reaction, you want from the reactants to the top of the hill. So that would be the distance between 2 and 1. Then we start to look at energy diagrams. And when it says energy diagrams, it means that we know the difference between endo and exo, as we've seen before. So if you have an endo energy diagram, then your reactants are lower than your products. If you have exothermic, then your products are higher. Your reactants are higher than your products. So with this example, it's asking which diagram, this one here, could the following reactions represent, or which reactions could be represented by that diagram. So we want to know that this is endothermic. So now these questions are essentially easy as long as you know that, because then we can go through. This one's exo, so not that one. Number 2 would be endo. Number 3 is exo because it's negative. Number 4 would be endo. Number 5 has the energy as a term on the product side, so that's exothermic, so not that one. Number 6 has the energy on the reactant side, so that would be endo. And then we have this last one that's positive, which is number 7, and the other one was not. So that one was 2, 4, 6, 7. So just re-entering with catalysts, they are just lowering the activation energy, but they do not affect the delta H. They don't affect anything else. It's just lowering that energy. So looking at this example, oftentimes catalysts are written above the arrow. So just being able to identify that. And then it's saying, what does the MnO2 represent? It's not going to increase activation energy. It would decrease it. Increase the energy released by the reaction. That's implying it has an effect on delta H, which it doesn't. Letter C, reduce the net energy released by the reaction. So same idea, it's acting like it's going to affect delta H, but it doesn't. And the last one, provide an alternate energy pathway for the reaction. That is our definitely our answer, but it does just lower that activation energy, makes that reaction happen faster. So the other part that we want to look at is Hess's law short, and then using Hess's law to find delta H and using it in another equation. So when we're doing this, it is called multi-step because you're doing more than one thing. So let's take a look at our reaction. This time we have the combustion of methane, but we don't have the delta H. So we're going to find that first. And then when it's asking about the energy released by methane, then we can use the formula that allows us to calculate that, which is NH equals delta H. So with this, we want to go through and actually figure out that value. So we would look for methane. Just thought I had my work shown here, but I guess I don't. I think I might have to skip this one for now because I don't have my data booklet, and I thought I had this one written out. Number 28. Yes, I don't. So just to go over that one more time. So you're using Hess's law short. So you'd look at your data booklet, get the heat of formation for methane. This one would be 0. Get the heat of formation for carbon dioxide. And then for water in the gas state, this one would need to be multiplied by 2. Then to find delta H of the reaction, you're going to get the sum of the products and subtract the sum of the reactants. Then whatever answer you get here, that's going into delta H of the formula. This 1.5 grams, we need to turn that into moles using the molar mass of methane. Then we can multiply to get that energy released. This says leftovers, but what we just want to go over is if you do have bonds breaking, you have to put in energy. So that would be endothermic. Bonds forming would be the opposite of that, so exothermic. Potential versus kinetic. It is potential if there's a chemical reaction. It's kinetic if you're heating or cooling. You have this concept of thermal stability. This is your species or compound being able to reduce being decomposed. So the more endothermic you are, the more you will reduce being decomposed. We have fuel efficiency, and that is just looking at, you don't see this that often, but if you do, you just want to make sure that you're burning what you're putting in. And then lastly, your experimental design. So understanding the manipulated, responding, and controlled variable. So here's an example with the variables. So we have a calorimetry experiment, and they're comparing how much or the enthalpy we get depending if we're burning methanol or ethanol, and each of these will have the same amount of mass. So just based on that, because you are comparing methanol and ethanol, that is your manipulated variable, because one of those experiments you would do with methanol, the second one with ethanol. Controlled is anything you keep the same. So you could control the calorimeter you're using. You can control maybe the room you do it in. There's many control variables that we can come up with. And then the last one, your responding, is what we're measuring. And in calorimetry, we are always looking for the temperature, right? That's what we're measuring. So going through this, manipulated is definitely the type of fuel. Controlled is not the temperature. Manipulated, type of fuel. Responding is the temperature change. That to me looks like the answer. Let's just check the rest. Controlled, type of fuel. Nope, that's manipulated. And D, controlled, variable in the mass. Nope, because it said it was equal. And this last one, taking a look, we have, again, calorimetry. We see that at the top. It tells us that we have the combustion of propane. And then it's also adding in here that the molar enthalpy of combustion is very different when it was calculated than the theoretical value. So your actual value, what you did in the lab, isn't matching what we should see. So trying to figure out what can reduce that discrepancy, they have a series of suggestions. So the first one, using a glass beaker to hold the water. Well, that should not matter because we have a container, and depending what we're using, we are accounting for that with the specific heat capacity of the container you use and the temperature change. So that one probably won't change it. Creating an open shield around the apparatus, that one is definitely going to be it. And that's because if this part, propane, is what's being combusted, we can be losing heat to the environment. When we want all of that heat that from this reaction to go into that water so that we can measure it. Now, if some of the heat is being lost, then our delta H won't be accurate. So by putting a shield around it, that would mean the heat that's coming off of this has nowhere else to go. So the water would be able to absorb it. So that should help. Let's just double check the rest. C, raising the calorimeter higher above the flame. If we moved this even higher up, that would be more of a distance for that heat to lose. So that's not going to work. And there's one more and I can't see it. So we do know the answer here is B. So I hope this helps. This is a good review of all of Thermochem. And if you do need any extra help or you have any suggestions, please just leave me a comment. If you watched this long, please subscribe and give me a like. Thanks for watching.